Okay, so for higher order equations with constant coefficients, we've already illustrated this. You assume solutions y equals ae to the RT. You get your characteristic equation. You solve the equation. You write out your solution set of n functions for equation of order n, because equation of order n is essentially you're solving for n derivatives. So you like do something that corresponds to integrating n times, and each time you get an arbitrary constant. And check. Wronskian for linear independence. General solution is an arbitrary linear combination of your solution set. And then you fit your constants to the situation. And you've already learned to do that in the earlier sections of the chapter. Now, I said before I started the recording, we're just going to do some examples. Okay, and well, say a little bit more. There are three scenarios for the characteristic equation. All real solutions implies all your solutions of the form e to the RT, obviously. With real numbers R. Okay. Need the word distinct in here. Okay. And all your R's are different. All real with repeated solutions implies you got to use reduction of order. If there are some complex conjugate solutions, The real solutions are still the form e to the RT. Complex solutions are the form e to the, just deciding what letters to use, say A plus IB T, and that's A e to the A plus or minus IBT. That would be complex conjugate solutions. The conjugate of A plus IB is A minus IB. And when you have complex solutions, they always occur in conjugate pairs. Now those forms are of e to the AT. Okay, that's an A there. It doesn't look much like one. Let's see if I can make it worse. E to the AT, e to the I BT, and e to the I theta is cosine theta plus I sine theta, the Euler identity with which I believe you're familiar from some other courses I know you've had since you had them with me. So that form would be e to the AT times the cosine of BT plus I sine of BT, and you get imaginary solutions. And I'm going to just digress for a minute. There's a really interesting article that I read in Quantum magazine. It's just online. If you just go to Quantum magazine, you can locate it. And I've sent you some articles, I think, from that. And I might well send you this one. We didn't do a whole lot of quantum mechanics, but we did circuits in which you got imaginary solutions to certain equations, and applied this. This I is a notational convenience, and it's always been regarded as a notational convenience. When you get into heavy-duty quantum mechanics with the Schrodinger equation, which is just a differential equation, but it's a partial differential equation and very difficult to solve in many cases, pretty easy for the hydrogen atom. I could explain to you how to do that, because that reduces to a set of ordinary differential equations with a very simple and intuitive substitution, change of variable, whatever you call it. You get a lot of imaginary solutions. It turns out that you don't have to use this notational convenience in differential equations and in general in mathematics, and all the way down to the most basic level we know of matter and energy and all that stuff. You don't have to do it, but it's extremely cumbersome if you don't. Okay, you can do it all with real numbers. You don't need imaginary numbers. Well, somebody's just hasn't yet published a paper. It's still being peer reviewed, but they claim, and they're very reputable, one of the top experimental team or top theoretical experimental. I don't know that much about the team. They've devised an experiment that seems very plausible. Nobody's done it yet, but we have the technique to do it. So somebody's probably going to pick up and run the experiment. It hasn't been run yet, but if the experiment works out the way it almost seems that it has to, it means that this eye actually has a physical reality, which is kind of neat. Okay, just something we made up. something was made up back in the 18th century, I believe, because it kept coming up in certain types of simple equations, like quadratic equations and so forth. Anyhow, it seems that instead of just a notational convenience, this might really be an irreducible aspect of physical reality. So I just toss that out now. It's pretty neat. The article's not all that technical, and my quantum mechanics is not up to the level of totally understanding how everything works out when you put everything into matrices and so forth. But the idea of the experiment isn't that obscure. Okay, well, anyhow, so this I might actually have some physical reality, not sure whether at the level of differential equations that really matters. It's a notational convenience, and we can treat it as such. It might be deeper than that. Okay, so anyhow, here's a picture of what you get, what you can get. So I'm just going to go ahead and, oops, I didn't wash that board. I wanted to use it, and I'm very likely going to need to use it because we can do a number of examples. And I might need all the board space I can muster. So give me just a second here. Yeah, I think I can get it further. Okay. Of course, I can't use that one, but I can use this one right now. Okay. Still got some space I can't use. I got to be careful about that. Okay. So example. And just an example of the type we've already seen. Y double prime plus 7y prime plus 10y equals 0. Now, these things aren't always equal to 0, but you always start, even if you have something over here that's not 0, you always start by doing the homogeneous equation, the equation that gives you 0, and we'll see why that is a little bit later. You let y equal e to the RT, and I'm not going to write it all out. You know that y double prime is r squared e to the RT. Y prime is r e to the RT, and 10y is just e to the RT. So every term here is going to have an e to the RT in it. And you can have an a e to the RT here. So every term would have an a e to the RT. You divide those out. Okay, e to the RT can't be 0, so you can safely divide it out. And you get an equation where the double prime comes out as an r squared, the prime comes out as an r, and the ae to the RT that makes up y when you divide through by ae to the RT just goes away, and just end up with the coefficient. And then you solve this equation. Now, when you have a cubic equation, you've got to go a little bit further, and you've got to try to find roots of that equation and do division and so forth. We'll do an example of that. It's basic pre-calculus that nobody remembers when they do differential equations. Your textbook, which is a fairly rigorous textbook, doesn't assume that you remember how to do that either. It shows you the rational roots theorem and its application and so forth. But anyhow, For a second order equation, we can always solve this by the quadratic formula, but in this case, it's easy to factor. That's r plus 5 times r plus 2, so that r equals -5 or -2. Okay, so there's your solution set. Now you've already done the section with Wronskians and so forth. So I'll just write out here. Be sure you check the Wronskian. For a simple equation like this, you can see that these are linearly independent. Sometimes it's not as obvious. So your general solution is this, because that's your general linear combination of the functions in your solution set. Okay, at this stage, given two initial and or boundary conditions, we get the specific which we also call a particular solution. And again, you've seen in preceding sections how to do that, so I'm not going to do that now. We've done examples of that. Okay, so does that make sense?
Yes.
Yeah, I'm pretty sure it would. Okay, so that's pretty straightforward. Okay, now over here we'll do another example. And I can't use 10. Gotta remember this stuff shows up way too prominently in the video. Okay, we got this equation. And we're going to let y equal a to the RT and see what we get. So I'll just say dots. We get r squared plus 5r plus 10 equals 0. No way we're going to factor that. The discriminant is 25 minus 40 is -15. So we're going to have a square root of -15. And that's going to, of course, give us a plus or minus square root of -15. And it's going to give us two complex solutions, complex conjugate solutions. So the solutions r equals -5/2 plus or minus square root of 15 over 2 times I. And you can use a quadratic formula as well as I can. So I don't need to explain how that comes about, assuming that I calculated that right, and I believe I did. Okay, if I didn't, well, one step that I failed to include here is this general solution really ought to be plugged back into your equation to see that it does give you 0. If you made a mistake in factoring this or in a clerical error or whatever, it'll show up. And it's always best to check by substituting this back into your equation. Doesn't take that long, saves pain later. Okay, so you get this. So your solution set is the set e to the negative 5/2 plus or minus the square root of 15/2 I t, and e, I have to write it a little low here too, negative 5/2 minus the square root of 15/2 t, close the braces, and now you can't read anything. So might as well leave it off the edge of the screen, but I'll pull it back. Okay, you understand what's going on here. And what's more important is what happens when we write this in terms of sines and cosines and exponentials. You see that here you're going to get an e to the negative 5/2 t times an e to the square root of 15/2 I t. I'm not going to go through the details because I kind of mentioned them here, and I don't think you're going to have any trouble with it. This gives you e to the negative 5/2 t times the cosine of square root of 15/2 t. And there's an I on this 15/2 too, but can't read it, so let's pretend. Well, there's one of your solutions. Put a big old comma here. And then we have e to the negative 5/2 t times the cosine of the square root of 15/2 t minus I sine of the square root of 15/2 t. Because of course, here you have the plus, here you have the minus on the imaginary part. Real part is the same in both cases. So your general solution C1 I'm going to write this out in a little more compact form. So I need something in front of that C1. I could squeeze it in, but let's go ahead and do it a little more neatly. Okay, so your general solution is going to be a C1 times this plus a C2 times this. Both of these have an e to the negative 5/2. So we're going to factor out e to the negative 5/2. 5/2 t. Okay, and then it's going to be times C1 times the cosine of square root of 15/2 t plus I sine square root of 15/2 t. And I need another parenthesis out here, so let's pretend it's there. Oh, sorry, I don't need another parenthesis. So let's make it look like it originally did. And then it's going to be plus C2 times the cosine of the square root of 15 halves t minus I sine of the square root of 15 halves t. And I'm going to note, and this is very important for the reality of your solutions, that C1 and C2 are complex constants. Okay. Now there's a lot more that we can say here, so I'm going to go ahead and say it as soon as I find what I'm looking for. There it is. So this general solution and that's the general solution that we have here, can be written as e to the negative 5 halves t times, okay, we're going to have a C1 plus C2 times the cosine of square root of 15 halves t, and then a C1 minus a C2 times the I sine of the square root of 15 halves t. Oh, you've got to watch smudges. Unsmudge the smudge. Important to have that I there, obviously. Okay, plus I times C1 minus C2 times the sine of. And you know what? I started writing the square root of 15 halves down here, didn't I? Oh boy. I'm going to have a couple of corrections to make. Should be square root of 15 over 2, not the square root of 15 halves. At this point, I was careless. And smudge aside, that's hard to read anyhow. We'll correct that. So I've got to correct these two. So excuse me a second. I have to take that whole expression out. And this one. It's nice not to make the errors. But if you're going to make them, I will say it's nice to remember how you got these things and be thinking about it as you're working. Even if you get to it late, you can save yourself some trouble, but try to avoid the error in the first place. In my case, I had just enough working memory to remember it. In a year from now, I don't think I'm going to have that. Okay, so anyhow, this general solution can be written this way. Now, C1 plus C2 can equal any real number. Meaning that if these are, remember, these are complex numbers, if they have equal and opposite imaginary parts, okay, and that's so if they have equal and opposite imaginary parts. C1 minus C2 can at the same time equal any imaginary number. Okay. I.e., got to be careful about my selection of letters here. I'm tempted to make this a negative I times C. And I'm going to do that because it comes out more elegantly. So now I can say for any real B and C, so your general solution can be e to the negative 5/2 t times a cosine of square root of 15 over 2t, not the square root of 15 halves. Started saying that, and then, you know, okay, that it's not a, hold on it. I'm going to use A in a minute, not just yet. Can be written like this, because you can solve this for any B and C. And of course, if C1 minus 2 is negative Ci, then you have a negative Ci here times I. Well, the I times negative I gives you 1, and you just get C. Okay. And you can easily convince yourself of that if it's not totally clear right now. Okay, so right there we've got our general solution. And now it's with real numbers. Now there's another way of saying this, which is just to say that your real part of this solution and your imaginary part are both solutions of the equation. Okay, the real part being any multiple of cosine of this thing and so forth. Okay, so here's your real part, here's your imaginary part, but now it's real. And this, now this is solution by. And this could equal e to the negative 5/2 t multiplied by a cosine of omega t. And this ought to start looking familiar to you if you think back 2 years to physics, second semester physics. This could be the angular frequency. And it's not negative 15/2 t, just negative 50, it's square root of 15/2. So let's get that smudge out of there. Okay, so that would be the angular frequency of a simple harmonic oscillator or circuit, mechanical oscillator or circuit. Among other things, but usually that's what's going to occur. Okay, so you have a cosine of omega t here. Omega is square root of 15/2, corresponding to an angular frequency. And the reason I didn't want to use a up here is because I knew I was going to come over around to here, and I want to use a for amplitude. Okay, a is the amplitude, and e to the negative 5/2 t is what I'm going to call your exponential attenuation factor. And that corresponds to having drag on a system. Drag being a resistance in a circuit, or a drag force due to a velocity in a mechanical circuit. So I'll just say that this amounts to something that occurs because of a drag force or resistance. Now, it's actually a pretty simple scheme. Again, as I say over here, if you have complex conjugate solutions, then you're going to get this sort of thing, okay? Because, again, to solve the equations, you get this. You use the Euler identity on this form of your solutions, and you get this. You observe, then you write your general solution with a constant in front of one solution, a constant in front of the other. And I've factored out the common term, because when you have a set of complex conjugate terms, the real part is going to be the same for both. It's like this, plus or minus this. Okay, the plus or minus then gives you the cosine and the sine. And it's obvious the way it works out. I don't want to say every possible word. Let you think them through. So general solution is this, since the general solution because of the fact that these are complex conjugates, C1 plus C2 can be any real number. C1 minus C2 can be any imaginary number. Specifically, C1 plus C2 could equal B. C1 minus C2 could equal negative C times I, where B and C are real numbers. Then everything else falls into place. And the step from here to here is just your basic trigonometry. Sum of two angles formulas and stuff like that allows you to put this into this form. And oh yeah, oh boy. Glad I went back over that. Hopefully you realize that something was missing here. Among other things, your omega is not an arbitrary constant. So a cosine of omega t, omega has to be square root 15 over 2 in this case. That's not an arbitrary constant. So we only had one arbitrary constant, what I wrote here, so that should have alerted me, and it might have alerted you. But you're trying to hopefully relate this back to something you learned a couple of years ago. This phi is your second arbitrary constant, and it's your phase angle. I don't have room to write it in here. And hopefully you remember how all this relates to the circular model. Okay, so it's like you're on your unit circle or your circle of radius A in this case, you expand that unit circle. The cosine gives you the x component of the point on the x-axis as your reference point moves around the reference circle. And phi tells you where you are at the beginning, which allows you to model any pendulum or any LRC circuit, basically. Okay, so I don't want to go too far into that. That can come out in some of the problems, but that's really a pretty complete connection to what we're trying to do in second semester physics. And I don't remember who mastered what, but I don't think anybody really mastered that part, even though people were able to do parts of it. Okay, so worth thinking about, especially if there's a chance that your engineering education might end up having to deal with mechanical or RLC circuits, mechanical systems or RLC circuits. And there are certainly other types of systems that exhibit that behavior, but those two are the most tangible. Okay, was there something else I wanted to say about this? Well, as you can see, there are more steps. If your discriminant here happens to be negative, but they're fairly straightforward and they all come down to this. You get this form or this form, but it's important to understand why. Okay. Now, the other example that we could do is repeated roots. But I'm not going to actually work all that through because we did that last time and it would be kind of redundant. And you say that you, and I'm confident that it's true that the whole method of reduction of order isn't a problem for you. So the third case would be, for example, y double prime plus 8y prime plus 16y equals 0. You get r equals -4 repeated root only gives you one solution. So we have this. So we let y equal u y1, which is u e to the -4t. Use reduction of order. You find that u equals t, so y2 is t e to the -4t, and you can work through those details. And actually, for constant coefficients, that's going to always be what you get, or at least a multiple of that, and you can always reduce it to this. Okay. I got any multiple of what you got here is going to be a solution. So it's safe to write this and totally skip reduction of order. On a test, I wouldn't want you to skip it. Unless you had other problems that do reduction of order, which you probably would. So maybe I'd overlook it. Depends on my mood, so don't skip it. Okay, now, in your general solution, or this linear combination, arbitrary linear combination. And you could always write that as e to the -4t times c1 plus c2t, if there's an advantage to doing that, sometimes there is. You can substitute this back in here and see that it works, and you should do that. Okay, so that's pretty much it for the basic things that you can do. Now I'm going to take a look at your homework to see if we've covered everything you need in order to do the homework. And if so, then I get to talk about, maybe start talking about what you do for non-homogeneous equations, which is actually fairly straightforward, but it comes out of reduction of order in kind of a neat way that you might have done on your homework. I don't remember. But it's related. And now that comes a little later. Okay, up in the bit on your homework. So I'm going to stop the recording for a minute. Okay. A third order system might yield a characteristic equation might yield this characteristic equation. Okay. Now, the problem is, if it looks like this, it's easy to solve. If you set this equal to 0, you find that r equals 2/3. You solve this, you find that r is 1 or 3. And very easy, but it's not going to look like this. It'll present itself as what you get when you multiply this out, and that's going to be r cubed. And then let's be careful, you got a negative 4r squared and a negative 2/3 r squared. Okay, well, that's going to be r squared minus 4, which is minus 12/3, and minus 2/3, that's minus 14/3 r. And then you're going to have 3r and negative 2/3 of 4r. Well, that's 3r and negative 8/3 of r. 3 is 9/3, so you have 9/3 minus 8/3. Should be r squared. And then minus 2/3 of r is minus 2. And that's disturbing. So you could get this, but you've got denominators, and it could be the equation is such that you don't have denominators, because this equation appears as 3r cubed minus 14r squared plus r minus multiplying by 3, 6 equals 0. Lost track. I don't know how that happened, but yeah, I do. Okay, so yeah, this is the same equation this is. Okay, now when you have the equation in this form, we don't have any denominators and so forth. Any rational roots of this are the form P over Q where P is a factor of negative 6. And Q is a factor of 3. Now we use 6 and 3 because 6 is over here. And it really doesn't matter that it's negative 6. I'll just say a factor of 6 because, well, and we'll stick with negative 6. Okay, and over here, you've got the 3. It's clear from the factored form that you get from an equation like this, that when you multiply the roots of the equation out, you're going to get this. Okay. And your denominator is going to be a factor of this. And I don't want to go into all that. So possible rational factors are what? Okay, well, your factors of 6 are 1, 2, 3, and 6. Factors of 3 are 1 and 3. So it's going to be plus or minus 1/1. And plus or minus will apply to any of these. 2/1, 3/1, 6/1. Because that's all the factors of -6 divided by factor 1 of 3. Okay, factor of 6 divided by factor of 3. Or another factor of 3 is 3. These are all the factors of 6. So it'd be 1/3, 2/3, 3/3, 6/3. Or plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6, plus or minus 1/3, plus or minus 2/3. And 3/3 is 1, we've already got that. 6/3 is 2, we've already got that. So these are all the possible roots. Now, we observe that if we plug in 1, we get 3 minus 14 plus 1 minus 6. And that doesn't work, but it should. So that means that I did something wrong. Real simple arithmetic. What's wrong here? 1 doesn't work. But 1 does work up here, because if you put 1 in here, you get 1 minus 4 plus 3. So when I multiply this by this, apparently I did something wrong. It doesn't affect this term or this term, so when I multiply by 3, it won't affect this or this. But something's wrong with these. So how did I get the r squared? Well, I have a -4 r squared. Sorry, -2/3 r squared and a -4 r squared. -4 is 12/3, -2/3 gives me -14/3, going to be -14 there. On r, it looks like I've got 8/3 and 3, and there it is. Okay, 3 is 9/3, so this should have been 17/3. And this should be 17r. I'm going to leave those smudges because this is pretty trivial stuff. But there's a 17, there's a 17. Okay. Now if I plug in 1, I get 3 minus 14 plus 17 minus 6. Well, your negatives are -14 and -6. Your positives are 3 and 17. The negatives -20, the positives +20, and it works. Okay. I got messed up with signs here. That's what happens when I do things in my head. So now it doesn't happen all the time right away, but I chose it this way so it would happen soon. Right away, r equals 1 works. So r minus 1 is a factor, which means r minus 1 divides this polynomial without remainder. Now, I'm not going to go through the long division, partly because I don't have time, partly because I don't have space. It's a long division. Looks like this. Okay. And up here you get quadratic polynomial. And that's the quotient. And the quotient, and you can verify it easily, is going to come out with roots r equals 2/3 and r equals 3. So that's generally how you deal with a higher order equation. You factor it, and part of what you need to know about factoring at this point is how to apply the rational roots theorem. It's something that you learned in pre-calculus, presumably, but haven't used since till now. I never learned it, but I got the differential equations, you know. Oh,
I was
use
hoping I
rational
would never
roots
have
theorem.
to use.
I'm sorry?
I was hoping I would never have to use it again. I remember that being my least favorite part of probably any math class I've taken. Not because it's difficult, just because it takes so long.
Yeah, you're right. It's not difficult, but it's kind of a pain. At the stage, you get it, okay? At the stage of a pre-calculus class, it seems like a real pain. And my pre-calculus students are, depending on the class, the accelerated class, 7-week class has already had that pain, and the other class is about to. Although I don't stress it that much, because I know that if they get to more advanced classes, by the time they get there, it's not going to look like such a pain because they have so much pain out of everything else. Okay. So at this stage, this isn't very painful, I don't think. You know, there are other things I want to stress in the pre-calculus class. You know, there are valid reasons for disagreeing with me on that, but I also have valid reasons for the things that I want to stress. Things that people never have when they come out of a pre-calculus class that really allow them to understand their calculus better. Okay. And I'm not sure who's right on that. It's maybe kind of a wash, because it's kind of a neat thing. When I saw it, which was, I mean, well beyond my calculus class, I think I might have been in advanced undergraduate courses, an abstract algebra course or something, when I first had to use the rational roots theorem. Might have used it in my differential equations class, but I'm not sure. You know, again, we had other things to worry about. Figuring out you learn to factor anytime. I mean, we had to do some fairly sophisticated factoring, so we probably did it in the differential equations. I found that to be a pretty easy course at the time. So I don't remember it being an obstacle. I remember seeing it, saying, oh, that's pretty neat. Why didn't I know that before? Well, because I never had a pre-calculus course. That's why. Okay. So I was having to conjecture a lot of stuff, but even not having had a pre-calculus course. I had extremely solid algebra and a good course in logic, which was sufficient and more. Okay, so anyhow, well, there it is. So that's pretty much what you need. Okay. Again, the problems at the end where you got to match the equation or find the differential equation that matches the solution. That's pretty straightforward if you understand the whole process, as I think you will by the time you get there. But again, if you have questions, email me as soon as I'm functional, which ought to be immediately. I'll be glad to answer you. Okay.
Okay. Thank you.
Okay. Well, if nothing else, I'll see you next time. I know you got to go to work.
Yeah.
And have a good one. Tell everybody I said hello.
I will. I'm sure Matt will be happy to hear from you.
Yeah, especially Matt. Tell him I said hi. How is he doing? Well?
Yeah, I don't work with him too much because he's a quality engineer and I'm in the engineering department. But we work together every once in a while, and I've shared a few stories from classes with you, with him, and he's shared a few stories from his time when he took classes with you. So he's a big fan of yours. He really liked your classes.
I'm a big fan of his. So tell him to holler at me when he has time. And
I will.
Know how things are going and how he's going to proceed in the future. Okay.
Okay.
Okay. Well, good to see you, Richard. And I'll see you next time.
See you Tuesday.